Tonight might be the moment everything changes. 3I Atlas, the visitor from another star, is now passing incredibly close to our Sun in what scientists are calling the ultimate test. If it speeds up or shows more energy than gravity alone can explain, then someone or something is definitely in control. That would be our first solid evidence of alien technology. If it's just a natural cosmic event, the mystery will continue. But if it's not natural, the universe just became a whole lot smaller. Stick with me as we break down all the possible outcomes and what they mean. Because by the end of tonight, our entire understanding of life, time, and even what it means to be human could be turned upside down. If this incredible mystery has you as captivated as it has me, please hit like and subscribe so you don't miss a single update as this all unfolds in real time. Drop a comment below to let me know where you're watching from, what time it is where you are, and share your thoughts on what might happen tonight. And if you want to help this community grow, please share this video on X, Facebook, Reddit, or even in your group chats. You're the reason we can keep digging into stories like this. So, thank you for always having our back. Part 1. The initial claim and the perihelion reality check. If 3I Atlas does what it might do tonight, nothing will ever be the same again. Right now, as you're listening, an object from far beyond our solar system is reaching the point in its journey around our Sun where it will be closest. We call this moment perihelion. And for this particular visitor, it's more than just another astronomical marker. This could be the moment humanity realizes we are not alone. Or it could be the moment we confirm that space is just as empty and indifferent as we've always feared. Either way, what happens in the next 72 to 240 hours will completely reshape our understanding of our place in the universe. The object we're talking about is officially known as C2025N1. It was discovered on July 1, 2025, by the Atlas Survey Telescope in Chile. Scientists have confirmed it's the third visitor from outside our solar system that we've ever detected, earning it the nickname 3I Atlas. Unlike comets that are born right here in our solar system, this object came from somewhere else entirely, carrying with it the frozen chemistry and maybe even the secrets of another star system. Its path tells us a lot about where it came from. Its orbit is what we call hyperbolic, meaning it will never come back. It's moving through our cosmic neighborhood at speeds that clearly show it's not from around here. Its extra speed is about 60 kilometers per second, which is far too fast for anything that's just gravitationally linked to our Sun. Tonight, October 29th, 2025, 3I Atlas reaches perihelion. That means it will be about 1.35 to 1.44 astronomical units from the Sun. To put that in perspective, that's roughly 203 to 210 million kilometers away, placing it somewhere between Earth's orbit and Mars' orbit. However, from our viewpoint on Earth, we face a frustrating problem. The object is in solar conjunction. This means it appears too close to the Sun in our sky to be seen directly. We can't watch it during these crucial hours. The Sun's overwhelming brightness completely washes out any attempt to photograph or track the object in real time. This forces us to rely on something else, something more subtle and potentially more revealing. We'll be looking for indirect evidence, which will only become clear in the hours and days that follow. What kind of indirect evidence are we talking about? Astronomers will be searching for tiny changes in its path that can't be explained by gravity alone. They'll be looking for extra heat that suggests active energy release, unusual patterns of gas and dust that don't match what natural comets do, or even the release of smaller objects that go into their own orbits. These would be the signs of something engineered, something controlled, something intentional. If 3I Atlas is more than just a stray piece of ice from interstellar space, if it holds technology or serves a purpose, then perihelion would be the perfect time to act. This is when its speed is at its peak, when it gets the maximum gravitational boost from our Sun, and when any applied thrust would make the biggest difference to its trajectory with the least amount of energy. Engineers call this the OTH effect, and if someone built this object, they would know exactly how to use it. The gap between what we see in the headlines and what scientists actually know has never been wider. News outlets have been buzzing with speculation for weeks. Some are suggesting this could be humanity's first encounter with alien technology. Avi Loeb, the Harvard astronomer who famously suggested that Oumuamua might be artificial, has made some provocative comments about unusual chemical signals. Online warnings have been circulating, with some claiming governments are covering things up or know more than they're letting on. Meanwhile, professional astronomers are urging caution, reminding us that extraordinary claims require extraordinary proof, and that we've been fooled by natural phenomena before. The space between these two viewpoints, between wild guessing and careful doubt, is where the truth will eventually surface. Consider what we already knew before tonight. Oumuamua, the first confirmed interstellar object found in 2017, sparked years of debate about its strange acceleration and long shape. Borisov, the second interstellar visitor discovered in 2019, behaved like a completely normal comet, easing some of the tension but also disappointing those who were hoping for something more unusual. Now we have 3I Atlas, and from the very beginning, it's presented puzzles that don't quite fit the usual pattern. Its orbit is almost perfectly aligned with the ecliptic plane, which is the flat disk where planets orbit our sun. This is statistically unlikely for a random visitor from the galaxy. Its composition shows oddities that some researchers find hard to explain through natural processes alone. And its timing, arriving at a time when humanity finally has the technology to detect and study such objects in detail, feels almost deliberate, though that might just be our own bias as a species desperate for cosmic neighbors. Over the next 72 to 240 hours, data will start flooding in from observatories all over the world and from spacecraft positioned throughout the solar system. Measurements of its position will pinpoint the object with millimeter precision, showing whether its path deviates from what gravity alone predicts. Spectroscopic observations will analyze the light reflecting off or being emitted by the object, looking for chemical signatures that point to artificial processes. Infrared telescopes will search for extra heat that could indicate active systems or propulsion. Radio telescopes will listen for any electromagnetic signals, no matter how faint, that might suggest intentional transmission. Each piece of data will either strengthen the case for a natural explanation or open the door to the possibility that we are witnessing something entirely unprecedented. The clock is ticking, and by the time you hear these words, perihelion may have already passed. We stand on the edge of discovery, caught between the comfortable idea that the universe is empty of other intelligent life and the terrifying, exhilarating prospect that we are being watched, studied, or at least noticed by an intelligence that has traveled between the stars. What happens next depends on what the data reveals, but also on how we interpret it, who controls the story, and whether humanity is ready to face the implications of contact, however indirect or ancient it might be. Part 2. First-order observations and the acid test metrics. The acid test for 3I Atlas comes down to numbers. Specifically, the numbers that describe how it moves through space. Astronomers will be examining something called delta V, which measures the change in velocity that cannot be explained by gravitational forces alone. Every object in the solar system follows a predictable path determined by the gravity of the sun and planets, and we can calculate that path with incredible accuracy. If 3I Atlas deviates from those predictions, even by a tiny amount sustained over days or weeks, we have a problem that needs an explanation. Natural comets do show small accelerations that aren't due to gravity, caused by gases escaping when sunlight heats their icy surfaces and releases jets of vapor that act like tiny rocket engines. The question is whether any deviation we see matches that natural pattern or suggests something else entirely. An Oth-style burn would leave a very specific mark in the orbital data. The Oth effect exploits the fact that kinetic energy increases with the square of velocity. This means a small thrust applied when you're moving the fastest creates a much larger change in total energy than you'd expect. Perihelion is when 3I Atlas is moving at its maximum speed relative to the sun, making it the ideal moment for any intentional maneuver. If the object fired an engine or released stored energy during these hours, we would expect to see its trajectory begin to shift in the days that follow, with the deviation growing larger as more data points are collected. The size of this effect matters enormously. A delta V of 1 millimeter per second would be barely detectable and could easily be mistaken for natural gas escape. But a delta V of 1 centimeter per second or more would demand serious attention and multiple independent confirmations before anyone would dare suggest artificial origins. Measuring such tiny deviations requires incredible accuracy in astrometry, which is the science of determining the positions and velocities of celestial objects. Ground-based telescopes can achieve positional accuracy of about 0.1 arc-seconds under ideal conditions. At the distance of 3I Atlas, that translates to uncertainties of hundreds of kilometers. That sounds imprecise, but when you track an object over multiple nights and use statistical methods to fit the observations to a predicted orbit, the accumulated data can reveal velocity changes at the millimeter per second level. The frequency of observations is important. More frequent measurements allow for faster detection of anomalies, but also increase the chance of errors creeping into the analysis. The observation windows also matter, because 3I Atlas must emerge from behind the Sun before we can resume tracking. Any delay in getting new data extends the period of uncertainty. Several instruments and tracking networks will be watching for these deviations. The Minor Planet Center coordinates astrometric observations from telescopes worldwide, collecting position measurements and calculating updated orbital solutions as new data arrives. Individual observatories contribute their own measurements, which are then checked against predictions to identify outliers or trends. Spacecraft missions operating in the inner solar system might be able to provide observations from different angles, offering parallax measurements that improve positional accuracy. Some missions carry instruments that are sensitive to heat or can image faint objects against the backdrop of stars. The key is redundancy. If multiple independent observers detect the same anomaly using different instruments and methods, the confidence in the detection rises dramatically. Astronomers will be creating what are called residual plots. These are graphs that show the difference between observed positions and predicted positions based on a purely gravitational model. In a perfect world where our model accounts for every force acting on the object, the residuals would scatter randomly around zero, just showing measurement noise. If instead the residuals show a steady trend, growing consistently in a particular direction over time, that indicates a real physical effect that our model isn't accounting for. Imagine a graph where each dot represents one night's observation, with the vertical axis showing how much the object's actual position differs from the prediction. If those dots start marching steadily upwards or downwards, curving away from the zero line in a consistent pattern, you have evidence of an anomaly. The challenge is to distinguish that signal from false alarms caused by errors in our models, unexpected pressure from sunlight, or subtle mistakes in the star catalogs we use to measure positions. False positives are a constant danger in this kind of analysis. Natural gas escaping from a comet can create accelerations that look like artificial propulsion, especially if the escape is uneven or happens in short bursts. Sunlight pressure, the gentle push from sunlight on any object with a large surface area compared to its mass, can also create small accelerations that must be carefully accounted for. Errors in our assumptions about the object's mass, shape, or how much it reflects light can affect the calculations and create fake anomalies. What separates a genuine engineered signature from these natural effects? The answer lies in the details. The direction of the acceleration relative to the Sun and the object's movement. The timing of any observed changes, whether there are any associated phenomena like dust clouds or heat emissions, and how consistent the effect is across multiple independent observations. Consider the possibility of seeing a plume that doesn't act like a comet's tail. Normal comet tails are broad and spread out, pushed away from the Sun by solar radiation and solar wind. They often split into separate dust and ion parts with different shapes. An engineered plume from a thruster might be narrow and directed, pointing in a direction unrelated to the Sun, lasting for a short time and then shutting off cleanly. If thermal imaging shows a hot spot that lasts longer than ice melting would predict or appears in a place that doesn't make sense for passive solar heating, that would warrant intense investigation. The infrared signature of an engine, even a small one, is different from the thermal glow of sunlit ice in ways that spectroscopy can potentially distinguish. The timeline for gathering this evidence involves several stages. The first data will arrive within hours of perihelion, once the object is visible again after being behind the sun. These initial measurements will be rough, limited by the object's position and brightness, but they will give us the first orbital solution after perihelion. Daily astrometric updates will refine that solution over the following week, gradually reducing the uncertainty and revealing whether any anomaly exists. Spacecraft observations, if any are planned, will arrive on their own schedules, determined by mission operations and data download times. Some critical measurements might not be available for days or even weeks, during which time speculation will run wild, and competing interpretations will spread through scientific communities and the media alike. What would cause astronomers to raise an alert? That depends on the size and clarity of the anomaly. A small deviation that barely rises above the background noise might lead to private discussions and trigger more observations, but no public statements until more data confirms or denies the signal. A large, undeniable deviation accompanied by unusual spectroscopic or thermal signatures would likely lead to rapid coordination through established networks, possibly triggering observations by major facilities and informal communication within the astronomical community. Before any official announcement, the line between justified caution and excessive secrecy will be tested in real time, with careers and reputations on the line depending on who claims what and when. Part 3. What we already have in hand. Catalog and imagery. Before we can even assess what might happen at perihelion, we need to understand what we already know about 3I Atlas from the months of observations leading up to this moment. The object officially carries the designation C2025N1 in the system managed by the Minor Planet Center. This is the international hub for observations of comets, asteroids, and other small bodies in the solar system. That designation tells us it was discovered in the first half of July 2025, making it a relatively recent addition to the catalog. The astrometric arc, which is the span of time over which the object has been observed and tracked, now covers several months, providing a solid foundation for calculating its orbit and reducing uncertainties. Those uncertainties still exist, of course, particularly for an object on such an extreme hyperbolic trajectory, but they have narrowed considerably as more data has been collected. The orbital parameters tell a striking story. Its eccentricity is about 6.14, confirming that this is no ordinary object captured by our solar system, but rather a true interstellar visitor. Objects bound to the Sun have eccentricities between 0 and 1, with 0 being a perfect circle and 1 being a parabola that just barely stays bound. Anything above 1 escapes entirely. And 6.14 represents a dramatically hyperbolic trajectory with an enormous amount of extra speed. That excess velocity, the speed at which the object is moving relative to the general motion of stars in our galaxy, is around 60 kilometers per second. To put that in perspective, Earth orbits the Sun at 30 kilometers per second, and to escape the solar system from Earth's orbit requires an additional 12 kilometers per second or so. This object arrived with enough speed to blast through our solar system like a bullet through fog, slowing only slightly as it swung around the Sun and then accelerating back out towards interstellar space. The inclination of the orbit is about 175 degrees. This means it's moving retrograde, in the opposite direction to how the planets orbit the Sun. That alone isn't particularly unusual for interstellar objects, as they arrive from random directions in the galaxy with no preference for our orbital plane. What is unusual, and what has raised eyebrows among researchers, is that the orbital plane is very close to the ecliptic. The ecliptic is the flat disk defined by Earth's orbit, and most of the other planets share it. The inclination is only about 5 degrees away from perfect alignment, which is statistically surprising for a random visitor. Most interstellar objects should arrive from arbitrary directions with inclinations spread out evenly across all possible angles. Finding one that happens to lie almost exactly within our planetary plane suggests either an incredible coincidence or some kind of selection effect that we don't yet understand. Or, as some have suggested, it implies that the object's trajectory was designed to make it easier to observe or interact with the planets. The images we have from observations before perihelion primarily come from the Hubble Space Telescope, led by astronomer David Jewett and his team. Hubble's sharp vision and sensitivity allowed for measurements of the object's nucleus size, though with considerable uncertainty due to the difficulty of separating the solid nucleus from the surrounding dust coma. The observations suggest a nucleus radius somewhere between 0.16 kilometers and 2.8 kilometers, a huge range that reflects the ambiguity in the data. Other estimates, based on different assumptions about albedo or how reflective the surface is, have pushed that upper limit even higher. The brightness of the dust coma indicates moderate activity levels before perihelion, consistent with ice sublimation, but not dramatically higher than other comets at similar distances from the Sun. Nothing in the basic photometry screams artificial, at least not on the surface. However, one measurement has generated significant discussion in recent weeks. Scientists are studying how light bounces off dust particles around Comet 3I Atlas. They've noticed something really strange at certain angles, a kind of extreme negative polarization. Think of it like this. Polarization tells us about the dust's size, shape, and what it's made of. Different materials leave different fingerprints. Most comets in our solar system have a predictable polarization pattern, showing us they're made of typical icy stuff with silicon and carbon. But 3I Atlas is different. Its polarization curve doesn't match the usual. Especially when the Sun is at a small angle, it shows this odd negative polarization. Researchers pointed this out in a new paper, but they were careful not to claim it's definite proof of anything weird. They suggested it might just mean the dust is unusual, or made of something we don't usually see in comets. Meanwhile, people online are sharing enhanced images of 3I Atlas, claiming to see strange shapes or structures. These enhanced images often involve heavy processing, boosting contrast and sharpening details. Sometimes this can reveal real features, but it can also create fake ones or make noise look like something solid. Without seeing the original, unedited data and understanding exactly how it was processed, it's impossible to say if these images show anything real. Professional astronomers are more reserved, releasing images that are carefully checked and analyzed. Their images tend to be less dramatic than what you see on social media. There's a big question mark over the comet's size, and this uncertainty makes it hard to interpret any odd behavior. If the nucleus is small, around 0.16 kilometers, its mass is low. Even a little bit of gas escaping or heat could cause noticeable changes in its speed. But if the nucleus is large, maybe 2.8 kilometers or more, it's much more massive. Any push not caused by gravity would need to be much stronger to have an effect. This size ambiguity creates a range of possibilities for its orbit. We have a good idea of its path, but how much solar radiation pressure or escaping gas will affect it depends on things we haven't pinned down yet. This leaves some room for minor deviations to be explained away as normal. However, a really big deviation would be impossible to ignore. Before it went behind the Sun, its predicted orbit had uncertainty bands, accounting for measurement errors and how we model it. These bands have gotten smaller as we've gathered more data, but they're still there. The most precise measurements came from just before solar conjunction, when we couldn't see it. Now that it's emerging from behind the Sun, telescopes will find 3I Atlas again and measure its position. The key question is whether its new position falls within the expected uncertainty range or outside of it, suggesting something unexpected happened while it was hidden. All of this background information is crucial because to understand any potential anomaly, we need to know what's considered normal versus what would be truly surprising. If the data shows a small change that fits within the known uncertainties, astronomers will likely just update their models. But if the data shows a significant, consistent deviation that can't be explained naturally, then we're in completely new territory, and the ultimate test will have revealed something truly remarkable. Now, let's talk about spacecraft and how we might track 3i Atlas. Besides ground telescopes, several spacecraft exploring the solar system might get a chance to observe 3i Atlas in the days and weeks after it passed its closest point to the Sun. These spacecraft weren't specifically looking for this comet, but their paths might put them in a position to gather valuable data if mission controllers decide to divert attention and resources. Each mission has limitations: power, data storage, communication schedules, other scientific priorities, and the risks involved in pointing instruments at an unexpected target. Whether any of these missions will actually observe 3i Atlas depends on decisions being made right now by mission operations teams, who are balancing scientific opportunity against the risks to their programs. The European Space Agency's JUICE mission, designed to explore Jupiter's icy moons, is on its way to Jupiter using a complex route. JUICE might have an observation window for 3i Atlas a few days after perihelion, depending on the spacecraft's exact location and orientation. JUICE has instruments for studying icy moons, but they can also be used for other targets. This includes cameras for taking pictures, spectrometers to analyze light, and potentially even radar to study surface properties. The challenge is coordinating these observations with the spacecraft's power and temperature limits, ensuring that pointing at an unexpected object doesn't disrupt critical operations or endanger sensitive equipment. Another significant opportunity arises around November 3, 2025, when 3i Atlas will pass Venus at a distance of about 97 million kilometers. While this distance is too great for Venus to be affected, spacecraft orbiting Venus or monitoring its environment might be able to observe it if their instruments are sensitive enough and have a wide enough view. Venus orbiters usually focus on studying the planet's atmosphere and magnetic field, but their cameras and spectrometers can sometimes be used for brief observations of passing objects. The geometry of this encounter is also important for tracking its path. If 3i Atlas released smaller objects or changed speed at perihelion, these effects might become more obvious as it passes Venus, and the deviation from its predicted orbit would grow larger. Earth's closest approach happens around December 19, 2025, at a distance of about 1.8 astronomical units, or roughly 270 million kilometers. This isn't a close encounter by human standards, but it's the best time for telescopes on Earth, both professional and amateur, in the northern and southern hemispheres, to gather high-quality data. December observations will benefit from months of accumulated trajectory data, allowing for very precise predictions of where the comet should be if only gravity were acting. Any deviation from that prediction will be very clear by mid-December, assuming the anomaly is significant enough to be real. This is also when spectroscopic studies can improve our understanding of the comet's composition, looking for chemical signatures that might have been missed or changed during its closest approach to the Sun. The most distant, but potentially most revealing encounter window is on March 16, 2026, when 3i Atlas will pass within about 54 million kilometers of Jupiter. NASA's Juno mission, which has been orbiting Jupiter since 2016, could potentially turn its instruments toward the comet if the geometry is right and mission controllers think it's worth the effort. Juno's cameras and spectrometers are designed to study Jupiter's atmosphere and magnetic field, but they've shown they can image other things, like Jupiter's moons and even distant asteroids. A Juno observation of 3i Atlas would offer a very different perspective than Earth-based observations, potentially revealing features or behaviors that are invisible from our planet. For each of these mission windows, the type of data collected depends on the instrument's capabilities and operational limits. Photometry, which measures brightness over time, can reveal how fast the comet is spinning, if it's experiencing outbursts, or if it's unexpectedly dimming, which could indicate it's breaking apart or shedding debris. Spectral composition analysis examines the wavelengths of light to identify specific molecules or minerals based on their unique absorption or emission patterns. Trajectory analysis benefits from any additional position measurements, especially from spacecraft far from Earth, as the parallax provides independent constraints on its orbit. Radio monitoring, if any spacecraft have the right receivers, could search for electromagnetic signals that might indicate technological activity. While the chances of detecting something are incredibly slim unless the object is actively transmitting, the limitations are real and numerous. The delay in communication between Earth and distant spacecraft means that any decision to redirect instruments must be made well in advance, often days or weeks before the observation window opens. There are restrictions on pointing to protect sensitive instruments from the sun or to maintain stable temperatures. Data transmission schedules are planned months ahead, and inserting unscheduled observations can delay other important science, causing friction within the mission team and among the broader scientific community that relies on that mission's data. Mission operations teams have to weigh the likelihood that 3I Atlas is genuinely unusual against the certain cost of diverting resources from planned observations. The timeline for these observations spans months, creating a story that unfolds slowly but surely. Perihelion is happening tonight, setting off a chain of events. The first 7 days after perihelion will bring the first observations from ground telescopes after it emerges from behind the sun, showing whether the object is still on its predicted path or has drifted. Mid-November will bring the alignment for the Venus flyby and potential spacecraft observations, if any have been scheduled. December marks Earth's closest approach and the peak time for follow-up observations by both amateur and professional astronomers. March 2026 offers the Jupiter window and a final chance for spacecraft observations before the object moves too far away to be easily observed. After that, months and years of tracking its position will continue, refining its orbit and looking for long-term deviations that might only become apparent over extended periods. Several risk factors complicate every step of this observation campaign. The predicted position of an object can gradually drift if our models don't account for all the relevant forces, a phenomenon known as ephemeris drift. Space weather events, especially solar storms that disrupt Earth's atmosphere or interfere with spacecraft operations, can delay or degrade observations. Scheduling conflicts arise when multiple high-priority targets compete for the same telescope time or spacecraft resources. Mission priorities can shift in response to unexpected discoveries elsewhere in the solar system, potentially pushing 3I Atlas further down the list of observations. Now, let's consider the immediate scenarios. Over the next 72 to 240 hours, we'll likely fall into one of 3 broad scenarios. Each has different implications and will require a different response from scientists and the public. Understanding these scenarios beforehand helps us interpret the data as it arrives and respond appropriately rather than reactively. These scenarios represent different levels of unusualness, ranging from completely natural to potentially extraordinary, with a middle ground of ambiguity where the evidence is suggestive but not conclusive. Scenario A. The natural case. In this scenario, 3I Atlas behaves exactly as we'd expect for an interstellar comet passing through perihelion. This would include breaking apart, increased gas and dust release as ice vaporizes under intense solar radiation, and small, non-gravitational pushes consistent with cometary jets. Its path would deviate slightly from predictions based purely on gravity, but this deviation would match models of cometary outgassing in both its strength and direction. No unusual heat signatures would appear beyond what passive solar heating would cause. No separate objects would be released into their own orbits. Spectroscopic observations would reveal a composition that, while perhaps different from typical solar system comets, could be explained by plausible astrophysical processes in the environment where it formed around another star. In this case, 3I Atlas would join the small but growing list of interstellar visitors, each teaching us about the diversity of planetary systems and how debris gets ejected into the galaxy, but none forcing us to consider the possibility of alien technology. Scenario B. The clear artificial signature. This is the opposite extreme, showing a distinct, undeniable engineered signature that cannot be explained by any known natural process. This would include a detectable change in velocity large enough to rule out cometary outgassing, pointing in a direction inconsistent with solar radiation pressure or natural jet activity. It might involve observing a narrow, focused plume during or shortly after perihelion, visible in infrared or optical light, lasting for a duration that suggests active control rather than passive ice sublimation. Excess heat emissions might appear in locations or at intensities that cannot be explained by solar heating alone. Separate objects could be released into trajectories that seem to be deliberately aimed at specific solar system destinations like Venus, Earth, or Jupiter. Spectroscopic analysis might reveal chemical signatures consistent with industrial processes rather than natural astrophysical chemistry, such as highly concentrated metallic compounds or molecular species that require energy to form. In this scenario, the chance that 3I Atlas is an artificial object would increase significantly, potentially forcing a fundamental shift in our understanding of our place in the universe. Scenario C, the ambiguous case. This scenario occupies a tricky middle ground, presenting something unexpected but not definitively conclusive. Perhaps the trajectory deviates more than expected from cometary outgassing, but not enough to completely rule out a rare or extreme natural event. Perhaps there are slight excess heat emissions that could be explained by unusual surface properties or low-level active systems. Perhaps separate objects are observed, but their paths are consistent with normal fragmentation rather than intentional targeting. Perhaps spectroscopic data show unusual chemical abundances, but not ones that are impossible through natural processes. In this scenario, astronomers would engage in passionate debates about interpretation, with some favoring exotic natural explanations and others arguing that artificial origins cannot be ruled out. Weeks and months would pass as more data is gathered, alternative models are tested, and the scientific community tries to reach a consensus. This is the scenario that tests institutional integrity, where the pressure to announce something exciting clashes with the professional obligation to remain cautious until the evidence is overwhelming. If scenario B occurs, if we genuinely detect an engineered signature, the response in the first 72 to 240 hours will be rapid and coordinated, but also chaotic and filled with uncertainty. Scientists who detect the anomaly will immediately check their data for errors, reanalyze it with different assumptions, and contact colleagues for independent confirmation. If multiple groups detect the same anomaly using different instruments and methods, confidence in the signal's reality will grow. At that point, institutional stakeholders must be notified. The International Asteroid Warning Network, NASA's Planetary Defense Coordination Office, ESA's Space Situational Awareness Program, and potentially even SETI organizations or astrobiology centers, depending on the nature of the signature. Who issues the first public alert will depend on institutional protocols and the individuals involved, but typically the Minor Planet Center or a major observatory might release a circular describing the anomaly without immediately claiming it as evidence of technology. Media attention will explode, regardless of how carefully the announcement is worded, forcing scientists into a reactive role as they try to explain complex uncertainties to journalists and the public. If scenario A occurs, if 3I Atlas behaves naturally, the narrative will shift to what we can learn from this visitor. Astronomers will declare it an interstellar comet with unusual but explainable properties, and the scientific community will begin preparing papers describing its composition, activity levels, and what these teach us about planetary systems around other stars. Proposals for future missions might emerge, suggesting that humanity should develop rapid response spacecraft capable of intercepting future interstellar visitors for close-up study. The public might be disappointed that alien technology wasn't discovered, but the scientific value remains high because every interstellar object offers a glimpse into environments we cannot directly observe. Scenario C, the ambiguous case, presents the greatest communication challenge. How do you convey genuine uncertainty to a public that demands clear answers? How do you maintain transparency without fueling conspiracy theories about cover-ups or institutional bias? The solution requires careful framing, explaining precisely what the data shows, what alternative explanations exist, what additional observations are needed to differentiate between them, and what the timeline looks like for reaching a conclusion. Lower third graphics in video presentations might display labels like preliminary data or multiple interpretations under review, to signal that conclusions are still tentative. Scientists must resist pressure to overstate the significance of ambiguous results, while also avoiding excessive caution that dismisses potentially important anomalies as mere noise. A newsroom checklist for covering this story over the coming weeks would include several key elements. First, identify the critical data streams: astrometric residuals from the Minor Planet Center, spectroscopic results from major observatories, spacecraft observation reports, if any emerge, and thermal imaging data from infrared telescopes. Second, establish relationships with institutional stakeholders who can provide authoritative information: NASA's Planetary Defense Office, ESA's Space Situational Awareness Coordinators, SETI Institute researchers, and academic groups at institutions with relevant expertise. Third, develop messaging frameworks that balance excitement with caution. Avoid hype that overstates the evidence, but don't dismiss genuinely anomalous results as mundane. Fourth, prepare for the long game, recognizing that definitive conclusions may take months or even years to emerge as accumulated data gradually narrows down the possibilities. Consider a specific rapid response scenario. If astrometric data reveals a velocity anomaly exceeding 5 millimeters per second in a direction inconsistent with cometary outgassing models, and if that anomaly is confirmed by 3 independent observatories within 48 hours of detection, then what happens next? If SETI detects something, they'll point more radio telescopes to search for signals that might point to technology. NASA or the European Space Agency might even assemble a special panel to see if any existing spacecraft can be redirected for a closer look. The International Astronomical Union might send out an alert to scientists everywhere, asking for more observations. Meanwhile, the media would go wild. Journalists would demand interviews, social media would buzz with speculation, and the public would want answers. Handling all this requires coordination among science groups, clear communication plans, and a shared understanding that extraordinary claims need extraordinary proof. Now, let's talk about the chemistry of Oumuamua, or rather, the object formerly known as Oumuamua. Its chemical makeup has baffled researchers since those first spectral readings came in months ago. We're going to explore what these chemical fingerprints tell us, what they don't tell us, and why some scientists struggle to explain them using just natural processes. Chemistry is like a signature for where something formed. It tells us about the temperature, pressure, radiation, and available elements from billions of years ago, when it was part of a protoplanetary disk. When we analyze the light from Oumuamua, we're essentially reading that signature and trying to match it to comets from our solar system or what we'd expect from other star systems. The most detailed analysis came from the X-Shooter instrument on the Very Large Telescope in Chile. Published recently in the journal Astronomy and Astrophysics, these observations showed unusual spectral lines. They didn't quite fit the standard comet profile. Normal comets give off light at specific wavelengths corresponding to common molecules like water vapor, carbon monoxide, carbon dioxide, cyanogen, and various carbon-based radicals. Oumuamua showed some of these expected features, confirming it has ice and dust like any proper comet. But it also showed anomalies in the amounts of certain substances and how those emissions changed as the object got closer to the Sun. The extremely negative polarization measurement we mentioned earlier adds another layer of oddness. Polarization tells us about dust grain properties, and negative polarization at small viewing angles usually requires a specific combination of particle size, shape, and refractive index that we just don't see in materials from our solar system. Polarization studies examine how light waves wiggle as they bounce off particles. Randomly scattered light becomes partially polarized, and how much and in what direction depends on the viewing angle and the properties of the particles. For most comets, the polarization curve follows a predictable pattern: slightly negative at very small angles, crossing zero, then positive, peaking, and then declining. Oumuamua deviated from this, showing a deeper negative polarization than expected. Some scientists think this indicates unusual dust composition, maybe grains with more metal or a different porousness than typical comet dust. Others suggest it might mean an unusual distribution of particle sizes, with a lot of grains in a specific size range that enhances negative polarization through something called coherent backscattering. The way its brightness changed, its photometric behavior, also provided clues. Dust production rates, measured by looking at the brightness and size of its coma, showed a relationship with its distance from the Sun that was slightly different from typical comets. Most comets brighten as they approach the Sun, following well-established rules that reflect how ice evaporation increases with temperature. Oumuamua followed a similar pattern, but with subtle differences in how its brightness changed with distance. These differences intrigued some researchers. They might simply reflect unusual ice composition or an odd distribution of ices just below the surface, where different ices evaporate at different temperatures and distances. Or they could hint at something more unusual. However, connecting brightness changes to engineered versus natural origins involves huge leaps of speculation. Several ideas try to explain these chemical and physical oddities within the realm of natural astrophysics. The first interpretation is that we're seeing a genuinely rare or extreme comet composition, reflecting the conditions where it formed around another star. Different stars have different metallicities, meaning different ratios of heavy elements to hydrogen. Comets formed in metal-rich disks might contain more refractory materials or unusual mineral types compared to our solar system's comets. The negative polarization anomaly might just be due to that compositional difference, revealing dust grains we've never encountered in our local collection of comets and asteroids. This explanation requires no exotic physics, just acknowledging the vast diversity of planetary systems in the galaxy. A second interpretation suggests Oumuamua might be a relic from an older generation of stars that formed billions of years ago when the galaxy had different chemical properties. The thick disk of the Milky Way contains older stars with different movements and compositions compared to the thin disk where our Sun is. Objects ejected from planetary systems in the thick disk might carry chemical signatures from that ancient environment, potentially explaining unusual abundance patterns or dust properties. This puts Oumuamua in a historical context, making it not just an interstellar visitor, but a time capsule from an earlier era of galactic evolution. The third, and most controversial interpretation suggests the possibility of engineered or manufactured materials producing the observed signatures. This idea is highly speculative and not supported by peer-reviewed scientific papers, but it has gained traction in some circles following public statements by Harvard astronomer Avi Loeb. Loeb has pointed to what he describes as unusual nickel emissions in the spectrum, suggesting the possibility of industrial compounds or refined metals rather than natural astrophysical materials. Some media reports have mentioned nickel tetracarbonyl, a volatile organometallic compound used in industrial nickel refining processes on Earth. While no peer-reviewed papers confirm its detection in Oumuamua, this claim remains unverified and should be treated with extreme skepticism until independent researchers can confirm the observation and rule out other explanations. Laboratory experiments help us understand what different compositions might look like in spectroscopic and polarization observations. Terrestrial industrial processes that create pure metal compounds follow well-defined chemical paths requiring specific conditions, controlled atmospheres, precise temperatures, catalysts, and energy input. Natural astrophysical environments can produce metal-rich materials through processes like condensation in stellar outflows or high-temperature chemistry in protoplanetary disks. However, the resulting materials typically show mixtures of phases and oxidation states rather than the pure single compound signatures characteristic of industrial processing. If spectroscopic analysis genuinely revealed highly pure metallic emissions without the expected oxidized forms or mixed phases, that would be difficult to explain through natural processes and would legitimately raise questions about artificial origins. The scientific framework for evaluating these competing hypotheses requires us to consider both how likely we are to observe certain data given each hypothesis and the prior probability we assign to each hypothesis before seeing the data. If we start with an extremely low prior probability for engineered origins, as most scientists do, then even moderately unusual chemical signatures won't significantly shift our belief towards the artificial hypothesis, unless those signatures are so extreme and specific that natural explanations become vanishingly unlikely. This is why the burden of proof is so high for extraordinary claims. Our starting assumptions matter, and overcoming a very low prior requires overwhelmingly strong evidence, not just suggestive anomalies. The question that keeps coming up is this: if you detect chemistry that significantly deviates from solar abundance patterns and from the range observed in solar system comets, at what point does that deviation become compelling evidence for non-natural origins? The answer depends on how well we understand the diversity of possible natural environments. Our sample size of comets from other star systems is tiny, just 3 confirmed objects so far. So we have almost no real basis for knowing what's normal versus unusual for interstellar visitors. Until we build that statistical foundation through future detections, every unusual measurement could either be a genuine anomaly, pointing to something extraordinary, or simply a reminder that the universe is more diverse than our limited local sample suggests. The chemistry puzzle connects directly to the propulsion question because any engineered thrust system would likely leave chemical signatures in its exhaust or waste heat. If Oumuamua is more than just a passive rock, if it contains systems capable of changing its trajectory, then those systems must produce observable effects: expelled propellant, thermal emissions, electromagnetic signatures, or structural changes. The chemical oddities we've observed so far don't conclusively point in either direction, but they establish that this object is unusual enough to warrant careful scrutiny as we search for mechanical or energetic signatures in the data from its journey after perihelion. Now, let's consider Part 7. If it's engineered propulsion architectures at 1.4 astronomical units. Suppose just for a moment that Oumuamua isn't a passive interstellar iceberg, but an object deliberately controlling its trajectory. What kind of propulsion system would be feasible near the Sun at 1.35 to 1.4 astronomical units? And what observable signatures would such a system produce? This question requires us to think through engineering constraints and possibilities, not because we have confirmed evidence of artificial propulsion, but because understanding what to look for helps us recognize it if it appears in the data. The challenge is enormous. Any propulsion system must operate in the extreme environment near the Sun, produce enough thrust for a detectable trajectory change, and do so using energy and propellant mass that the object can carry or generate. High specific impulse chemical propulsion is the simplest and most familiar architecture, similar to rocket engines used in human spaceflight. A chemical rocket combines fuel and oxidizer, releases energy through combustion, and expels hot exhaust at high velocity to generate thrust. Specific impulse, measured in seconds, tells us how efficient the engine is. Higher values mean more thrust from each kilogram of propellant. Chemical rockets typically achieve specific impulses between 200 and 450 seconds, which is respectable for maneuvering spacecraft, but requires substantial propellant mass for large velocity changes. If Oumuamua carried a chemical propulsion system and fired it at perihelion, we would expect to see a narrow, directed plume of hot gas expelled in the opposite direction of the desired thrust. The exhaust would glow in infrared wavelengths due to its high temperature, potentially creating an observable thermal signature lasting minutes to hours, depending on how long it fired. Astrometric measurements would reveal a sudden velocity change in the predicted direction, becoming larger over the following days as the object followed its altered path. Pulsed thermal engines are a more exotic option that uses solar energy instead of stored chemical energy. A solar thermal rocket uses mirrors or lenses to focus sunlight onto a heating chamber, raising the temperature of a working fluid that then expands through a nozzle to generate thrust. At 1.4 AU, sunlight is less intense than in Earth's orbit, but still substantial, around 500 watts per square meter. A large enough collector area could gather megawatts of power, heating propellant to temperatures high enough for useful specific impulse. The advantage of solar thermal propulsion is not needing to carry fuel, only propellant mass, and potentially using any volatile material, even water ice or carbon dioxide, sublimating from the object's own surface. Observable signatures would include thermal emissions from the collector surface, directional outgassing as propellant expands through the nozzle, and trajectory changes consistent with the thrust vector. The challenge is building a system with sufficient collector and thermal engineering to handle the concentrated sunlight without melting or degrading. Directed mass ejection through electromagnetic acceleration offers another speculative possibility. A mass driver or railgun uses electromagnetic forces to accelerate projectiles to high velocity, expelling them to generate thrust through conservation of momentum. Unlike chemical or thermal rockets that expel hot gas, a mass driver launches solid or liquid pellets at velocities potentially reaching kilometers per second. The specific impulse can be very high, meaning less propellant mass is needed for a given velocity change, but the system requires substantial electrical power to operate. At perihelion, solar panels could potentially generate that power, converting sunlight into electricity that drives the acceleration system. Observable signatures would include the expelled mass itself, potentially visible as a stream of small particles trailing the object, and electromagnetic emissions associated with the acceleration pulses. Trajectory analysis would reveal velocity changes consistent with momentum transfer from expelled mass. Beam-driven propulsion represents an even more speculative architecture where external energy beams, possibly lasers or particle beams, illuminate the object and impart momentum through radiation pressure or ablation. This scenario requires infrastructure elsewhere in the solar system or in nearby interstellar space. A powerful transmitter capable of delivering megawatts or gigawatts of power across astronomical distances and maintaining precise targeting of a fast-moving object. The advantage is that the object itself doesn't need to carry fuel or power systems, only a surface capable of absorbing or reflecting the beam efficiently. Observable signatures might include unexpected heating on one side of the object, asymmetric thermal emissions, or small but sustained accelerations in a consistent direction over extended periods. This architecture seems unlikely given the enormous distances and energies involved, but we include it for completeness because ruling it out requires understanding what we should or shouldn't observe. For each propulsion concept, we can estimate the required energy budget and compare it to what's physically plausible. Consider a change in velocity of 1 centimeter per second applied at perihelion to an object with a mass of 1 × 10 to the power of 15 kilograms, roughly consistent with a nucleus radius of 1 kilometer and typical cometary density. The kinetic energy change equals 1/2 times mass times velocity change squared, yielding approximately 1 × 10 to the power of 11 joules. That's a modest energy compared to, say, chemical explosives or nuclear reactions, but it must be delivered in a controlled, directional manner. Chemical propellant could provide that energy if the object carried sufficient fuel, perhaps a few % of its total mass, depending on specific impulse. Solar thermal propulsion could deliver it over a longer burn duration using concentrated sunlight. The key question is whether any plausible natural process could mimic those signatures. Outgassing jets can produce accelerations in that range, but typically with different temporal profiles and directional properties than engineered thrust. The waste heat signature matters enormously for detection. Any propulsion system operates with less than perfect efficiency, converting only a fraction of input energy into useful kinetic energy, while the remainder becomes waste heat that must be radiated away. A chemical rocket at typical temperatures radiates predominantly in the mid-infrared, around 3 to 15 microns wavelength. Solar thermal systems have cooler exhaust and hotter collector surfaces, potentially showing distinct thermal signatures in multiple infrared bands. Mass drivers generate waste heat in the acceleration system and potentially in the expelled projectiles if they're heated during launch. Beam-driven systems heat the illuminated surface, creating hotspots that radiate thermally. Each of these heat sources produces characteristic spectral signatures that infrared spectroscopy can potentially distinguish from passive solar heating of an inert surface. Plume geometry provides another diagnostic. Natural cometary jets are typically broad and chaotic, driven by sublimation from multiple active regions on the nucleus, with dust and gas expanding radially away from the surface and then being pushed by solar radiation pressure and the solar wind. An engineered plume from a thruster should be more columnated, expanding in a cone with an opening angle determined by nozzle design, potentially showing shock structures or density gradients characteristic of supersonic flow. High-resolution imaging during or shortly after a burn might reveal these geometric differences, allowing us to distinguish between passive outgassing and active propulsion. The directionality matters too. Cometary jets typically point away from the sun because that's where sunlight heats the surface most intensely, while engineered thrust can point in any direction depending on mission requirements. Potential debris or secondary ejector complicates the picture. If an object fires a propulsion system, especially one involving mechanical components or high-energy processes, it might shed fragments or expel material not intended as propellant. These debris pieces would follow ballistic trajectories determined by their ejection velocity in the gravitational field, potentially becoming detectable as small objects orbiting independently or trailing behind the primary object. Finding such debris would be strong evidence of mechanical activity, though distinguishing it from natural fragmentation requires careful analysis of the debris trajectories and compositions. The objection that arises immediately is, if this object is engineered, why would it hide its capabilities? Why not transmit signals or perform maneuvers so obvious that we couldn't miss them? Several answers exist, though all are speculative. Perhaps the object is old and damaged, operating with minimal functionality rather than full design capability. Perhaps it's designed for stealth, minimizing detectable signatures to avoid attracting attention from potential threats. Perhaps the mission isn't about talking to alien civilizations, but simply watching and collecting data, whether we notice or not. Maybe their actions are obvious to advanced beings, but we just don't have the right tools or knowledge to see them. Either way, these ideas require us to guess about alien goals and abilities, which we can't prove. That's why we need evidence, not just speculation about why they might be doing something. Now, we enter a more imaginative, almost science fiction realm, but one that deserves careful thought. What if 3 Atlas isn't just passing through, but actively dropping smaller objects, like tiny probes or sensors, into orbits aimed at specific places? Venus, Earth, Mars, or Jupiter? What would that look like? How would we even find them? And what would these scattered objects do when they reached their targets? These questions mix engineering with deep speculation about alien intentions, a scenario explored for decades in fiction, but one that real science must approach with extreme caution. This scenario starts with a release event near 3I Atlas's closest approach to the Sun. That's when it's in the perfect spot to launch objects that can reach destinations in the inner or outer solar system with very little extra push. The oath effect works in reverse here. A tiny change in speed at this point, when velocities are highest, creates a big energy change, opening up many possible paths. A release speed of just a few meters per second could send fragments on paths that cross planetary orbits months or years later, depending on the direction and timing. The real challenge is hitting a specific target. To reach a particular planet on a precise date, you need to calculate the release very carefully and perhaps make adjustments along the way. By studying the orbital mechanics, we can work backward to figure out what release conditions would be needed to intercept Venus, Earth, or Jupiter during the times we're looking for them. An encounter with Venus happens around November 3rd, just 5 days after its closest solar approach, at a distance of 97 million kilometers. For a small object released then to reach that point, it would need a slight nudge to change its path and timing so it crosses Venus's orbit at the right moment. The amount of speed change needed depends on where Venus is at that exact time, but estimates suggest a few to tens of meters per second would be enough. That's easily achievable with simple mechanical launchers, like a spring-loaded device, a small gas thruster, or even by directing gas released from the object itself. The Jupiter encounter, scheduled for March 16, 2026, is much further off and requires different orbital calculations. An object released at perihelion with the right speed could enter an orbit with a slightly different shape and size. This would allow it to reach its farthest point from the Sun, near Jupiter's orbit, around the same time Jupiter is passing through that area. The speed change required increases with the accuracy needed for targeting. Hitting within 1,000,000 kilometers of Jupiter is fairly easy, but getting within 100,000 kilometers needs more precision and possibly a larger speed change. An interesting question arises. Would these released objects just fly by Jupiter, or would they actively try to meet specific moons, like Europa or Ganymede, where underground oceans might support life? Getting close to a moon would demand significantly more speed change and much more advanced navigation. What we might expect to see from such a mission depends heavily on the size and number of objects released. If we're talking about dust-sized particles, they'd be practically invisible unless they were incredibly numerous or happened to pass very close to Earth or a spacecraft. If they were between a centimeter and a meter in size, we might detect them by the sunlight they reflect or the heat they give off, but only with dedicated searches using sensitive equipment. If the objects were much larger, tens of meters across, they'd show up in sky surveys as new asteroids or comet fragments, setting off alarms in automated detection systems. The way the trailing debris cloud forms would give us clues. A natural breakup usually creates a cloud of particles that spreads out slowly along the object's original path. However, if multiple objects were released on different paths, it would create a more complex, uneven distribution. Astronomers, both professional and amateur, could search for this debris in several ways. Enhanced brightness measurements around the time of the Venus approach could reveal sudden changes in light or new points of light appearing near where 3i Atlas is expected to be, or slightly off to the side, consistent with an object released earlier. Radar observations from systems like the Arecibo Observatory, if it were working, or the Goldstone facility, could detect small objects passing within a few million kilometers of Earth by bouncing radio waves off them. Occultation searches involve watching bright stars for brief dimming events caused by foreground objects passing in front of them, potentially revealing otherwise unseen debris. Automated sky surveys that repeatedly photograph large areas of the sky could spot moving objects not seen in earlier images, prompting follow-up observations to determine their orbits. The scale of such an operation remains pure guesswork. Are we imagining thousands of microprobes scattered across the solar system? Or perhaps a few dozen carefully placed sensors targeting key locations? Or maybe just a single probe aimed at Earth, with the rest being natural fragments? Each possibility would create different observable signs and require different levels of technological sophistication. Thousands of objects would suggest an industrial-scale capability, perhaps a civilization accustomed to sending massive survey missions. A few objects might indicate a more focused, efficient approach, prioritizing specific destinations based on prior knowledge. The number of objects also affects how likely we are to detect something. More objects mean more chances for one to pass close enough to Earth or a spacecraft to be noticed, and also more chances for amateur astronomers to spot something unusual. Could existing spacecraft be redirected to look for strange small objects near Venus or Jupiter during the relevant times? In theory, yes. But in practice, it's incredibly difficult. Spacecraft cameras and instruments have limited fields of view and must be aimed precisely at targets to gather useful information. Searching for unknown objects in the vast space around a planet would require either systematic surveys covering large areas, which are time-consuming and generate a lot of data, or prior knowledge of where to look, which we wouldn't have unless ground-based observations provided rough locations. The missions currently operating near Venus and Jupiter were designed for planetary science, not for hunting debris, and their schedules are already packed months in advance with observations of the planets and moons they were sent to study. Redirecting resources to search for speculative debris would require convincing mission managers that the chances of finding something interesting justify the loss of planetary science data. We can't avoid the question of why this would happen, even though answering it requires us to assume alien psychology and decision-making. Why would an advanced civilization send microprobes from an interstellar object passing through a planetary system? The most obvious answer is reconnaissance. gathering data about planetary environments, atmospheric compositions, surface conditions, and potentially signs of life if it exists. A more literal seeding might involve dropping self-replicating machines that establish a permanent presence, collecting data for centuries or millennia, and possibly sending it back to their home civilization using methods we can't even imagine yet. Communication relay nodes could create a network for real-time or near-real-time monitoring of the system, though real-time is a bit misleading given the vast distances signals would have to travel between stars. Each of these ideas assumes that this civilization values knowledge about other planetary systems. This is a reasonable assumption, given that we value such knowledge ourselves, but it remains impossible to verify. The most unsettling thought is that we might be misunderstanding the whole situation, projecting our own motives for exploration onto phenomena that operate on completely different principles. Perhaps the object isn't exploring at all, but serving some industrial or logistical purpose we can't comprehend. It could be collecting specific materials from the solar environment, disposing of waste from some interstellar operation, or testing technologies in the harsh conditions near a star. Or perhaps the released objects aren't probes at all, but byproducts of natural processes we haven't fully understood yet. Unusual gas releases or electrical events that produce signals that coincidentally resemble engineered deployments. To tell the difference, we need not only to detect anomalies, but also to understand the mechanisms behind them, proving that natural explanations don't fit before we consider extraordinary interpretations. The social side of this story is as important as the technical details. How humanity reacts to unclear evidence depends greatly on institutions, individuals, and the complex web of incentives that shape how science is communicated and how the public understands it. The possibility that 3I Atlas is more than just a natural comet triggers dynamics that go far beyond typical astronomical research. It taps into deep-seated hopes and fears about contact with alien intelligence, tests the resilience of scientific institutions designed for gradual discoveries rather than earth-shattering revelations, and exposes the gaps between expert consensus and public speculation. Understanding these dynamics can help us anticipate what might happen in the coming days and weeks, no matter what the data eventually reveals. Public fascination with claims of alien technology has grown significantly in the past decade. This has been fueled by the Oumuamua controversy, a renewed interest in unidentified aerial phenomena following government declassifications, and the increasing number of exoplanets discovered, proving that planets around other stars are common. Skepticism has also evolved, with many people automatically dismissing extraordinary claims as misidentified natural phenomena or outright hoaxes, while others enthusiastically embrace them, interpreting any ambiguity as confirmation of their existing beliefs. The Oumuamua debate set a precedent. Avi Lowe, a Harvard astronomer, publicly suggested that the object's unusual acceleration might point to artificial origins, perhaps a light sail or some other technology. While most astronomers argued that natural gas release was a simpler explanation requiring no unusual physics, the debate raged across scientific journals, popular media, and social media, with passionate supporters on both sides and a large group of researchers who found the controversy more distracting than illuminating. The network of organizations and communities involved in tracking and responding to anomalies like 3I Atlas, each with its own priorities and limitations, is quite broad. Professional astronomers at research institutions and observatories conduct the observations and analysis that produce the raw data. They are driven by scientific curiosity, the desire for career advancement through publications, and the intellectual challenge of understanding unusual phenomena. The Minor Planets Center coordinates efforts to measure object positions worldwide, collecting data from observatories and computing updated orbital solutions to track their movements. The International Asteroid Warning Network, established to coordinate responses to potentially hazardous asteroids, provides a framework for quick communication and data sharing when unusual objects are detected. Although its primary focus is on impact risk rather than technological signatures, NASA's Planetary Defense Coordination Office and ESA's Space Situational Awareness Program monitor near-Earth objects and coordinate international responses, bringing governmental resources and institutional credibility to the effort. SETI organizations and astrobiology centers hold a unique position in this network, specifically focused on searching for evidence of extraterrestrial intelligence or life. These institutions have developed protocols and technical capabilities for detecting potential techno-signatures, from radio transmissions to optical laser pulses. They also maintain relationships with observatories that can be activated when interesting targets emerge. Their challenge lies in balancing the genuine scientific search for intelligence against the risk of being associated with fringe speculation or pseudoscience, a reputational threat that makes many SETI researchers very cautious about public claims. Media influencers and private space enthusiasts add another layer to this network, amplifying certain interpretations and shaping narratives that may or may not align with scientific consensus. Avi Lowe, for example, has built a significant public platform partly by being willing to discuss exotic possibilities that most astronomers avoid, attracting both admirers who appreciate his intellectual courage and critics who accuse him of seeking attention through sensationalism. Formal tracking and reporting practices follow established protocols that balance the need for rapid communication with the requirement for data quality and verification. When an observer detects an unusual object or notices strange behavior in a known object, they typically report it to the Minor Planet Center using standardized formats that include position measurements, timestamps, observer details, and preliminary orbital calculations. Staff at the Minor Planet Center review these reports, check them for errors, and if satisfied, add them to the official database, possibly issuing an announcement about the discovery or unusual activity. Emerging anomalies that might suggest something beyond normal cometary or asteroid behavior trigger informal communications among researchers, often through email lists or collaboration platforms where experts share preliminary findings and coordinate further observations. Official announcements are held back until multiple independent confirmations establish that the anomaly is real and not an artifact of measurement errors or data processing mistakes. Some claims circulating online about 3I Atlas have not been verified through these official channels. Reports of unusual colors, descriptions of the object as being the size of Manhattan, and assertions that it is on special watch lists maintained by NASA or other organizations lack direct institutional documentation for confirmation. This doesn't necessarily mean the claims are false, but they should be treated with caution until supporting evidence emerges. The problem is that once unverified claims spread widely, especially through social media platforms where attention and engagement drive visibility, they can shape public perception and create pressure on institutions to respond, even when the underlying information is questionable. Scientists then face a difficult choice: ignore the claims and risk being accused of a cover-up, or address them directly and potentially give them more attention and legitimacy than they deserve. The tension between transparency and caution affects every aspect of how institutions manage potentially extraordinary discoveries. Transparency means sharing data and findings openly, allowing for independent verification and building public trust by being honest about what is known and unknown. Caution means withholding announcements until the evidence reaches a high level of confidence, thereby avoiding false alarms that damage credibility and cause confusion. When data shows something odd, something that doesn't fit standard models but isn't yet conclusive, institutions face real dilemmas about what to say and when. Delaying announcements to allow for verification can fuel speculation about cover-ups or conspiracies, especially if rumors leak through informal channels before official statements are made. Rushing to announce preliminary findings risks turning noise into a signal, transforming measurement artifacts or rare natural phenomena into major controversies that consume time and resources to resolve. Historical examples highlight both the dangers and the potential of these dynamics. Fast radio bursts, for instance, initially sparked speculation about alien signals because the bursts appeared to show temporal patterns that some interpreted as artificial. However, further observations revealed that most, if not all, originated from natural astrophysical sources like magnetars. The supposed detection of phosphine in Venus's atmosphere caused intense excitement about possible biological activity, but subsequent reanalysis cast doubt on whether the detection was real or resulted from data processing choices and instrumental artifacts. The SETI false alarm from BLC-1, a candidate radio signal detected by the Breakthrough Listen project, generated brief, intense interest before being traced to human-generated interference rather than an extraterrestrial transmission. Each case demonstrates how initial excitement must give way to careful verification before conclusions are solidified. The motives driving different players in this system vary considerably. For individual researchers, being the first to detect or correctly interpret something extraordinary brings immense professional rewards. Publications in prestigious journals, invitations to conferences and media appearances, an enhanced reputation among peers, and potentially long-term career advantages. The downside is the reputational damage from making claims that don't withstand scrutiny, being remembered as the person who cried alien when the truth was far more ordinary. For institutions, incentives favor caution because credibility built over decades can be destroyed by a single, high-profile mistake. The media, on the other hand, is rewarded for attention and engagement rather than accuracy, which can create pressure to hype ambiguous results or frame stories in ways that maximize emotional impact rather than careful understanding. Speculative scenarios involving internal conflicts or competing agendas add another layer of uncertainty. What if one group of observers spots something unusual, but decides to wait for spacecraft data to confirm it before saying anything? What if companies investing in interstellar missions push for public excitement to get money, even when the evidence is unclear? What if government agencies with secret tools know more but stay silent for national security reasons, or because confirming strange claims outside normal science would be too disruptive? These ideas are mostly guesswork, not proven facts, but they show how power, information, and institutions affect what we learn. The pictures and documents connected to any unfolding story are crucial for how people understand it. Looking back at old scientific arguments, like the fuss over cold fusion or claims of alien bacteria in Martian rocks, reminds us that the line between groundbreaking discovery and embarrassing mistake is often only clear later. Media headlines swing between blind enthusiasm and harsh doubt, rarely hitting the balanced middle ground where most real scientific progress happens. Screenshots of official websites and reports offer solid proof, letting people check claims against the original sources instead of just relying on others' interpretations. Interviews with astronomers who sound both cautious and curious reveal that scientists don't all agree, and reaching consensus on controversial topics isn't easy. The whole drama of how data is gathered, understood, and shared matters, even if 3 Atlas turns out to be completely natural. It shows how ready or unprepared we are for truly strange discoveries. The rules we create, the ways we communicate, and the transparency we demand will all shape our reaction when, someday, we find something that can't be explained by nature alone. Building this system takes practice, learning from close calls and false alarms, getting better at sorting important signals from background noise, and communicating uncertainty without freezing up or jumping to conclusions too soon. Part 10 tackles the hardest question: intent and interpretation. Imagine waking up tomorrow to confirmed data showing a small but significant anomaly in the path of 3-eyed Atlas. Something not explained by natural gas leaks or calculation errors. Something that truly hints at intelligent direction. What then? How do we figure out intent from mere observation? How do we go from noticing a strangeness to understanding its purpose, its reason for being, or the intelligence behind it? These questions get to the heart of the biggest challenges in searching for alien life, forcing us to consider how much we can truly understand about minds vastly different from our own, based on limited physical clues. The answers are vital because they influence how humanity would react, what dangers we might face, and what opportunities might arise if contact, even indirect, has indeed occurred. A chain of reasoning connects raw observation to understood meaning. Each link requires assumptions and judgments that become more speculative the higher you climb. The first step is the anomaly itself, a measured deviation from expected movement, extra heat, or a chemical makeup that doesn't fit known natural processes. This step needs careful statistics and error checks, but it's mostly objective and can be answered with standard science. The second step is about its size, direction, and timing. How big is the anomaly? Where is it heading? When did it happen? These details offer clues about the cause, narrowing down possibilities to natural or artificial explanations. The third step is about possible motive. If the anomaly is the result of deliberate action, what goal might it serve? This is where real speculation begins, because figuring out purpose means trying to model the thinking of an intelligence whose history, technology, and values are completely unknown to us. Potential motives cover a wide range of ideas, each leading to different predictions about what we should see. A probe designed to observe would focus on gathering data about our solar system, its planets, and possibly its inhabitants, using sensors to record radio waves, atmospheric makeup, surface features, and any signs of technology or life. Such a probe might stay hidden, avoiding actions that would reveal its presence. Or it could actively send data back to its home civilization using lasers or radio signals. A network of remote sensors could involve several objects spread out to cover the entire solar system, pinpointing interesting events or tracking long-term changes over years or decades. Reconnaissance implies a more active mission with specific intelligence goals, perhaps checking planets for habitability, listing resources, or even assessing the technological level of any civilizations present. Seeding or leaving a trail suggests a longer-term strategy, where the visiting object leaves behind monitors or artifacts that remain in the solar system after the main object departs, creating a lasting presence that continues to function long after the initial encounter. These monitors might activate under specific conditions, like detecting radio signals characteristic of a technological civilization, or they might record data constantly, storing it for later retrieval or transmission. The advantage of seeding is having backups and broad coverage. Multiple monitors in different locations provide redundancy and complementary viewpoints, ensuring that if some fail or are destroyed, others continue the mission. Test beds or experimental scenarios suggest the object is actively changing conditions or observing reactions to stimuli, treating the solar system as a laboratory to study planetary system dynamics, the origins of life, or perhaps societal responses to contact. Acting as a communication relay or signal repeater would allow the object to serve as infrastructure for interstellar communication, either passing messages between distant civilizations or acting as a navigation beacon that helps other objects find their way through space. This interpretation assumes the existence of larger networks or traffic patterns we haven't detected, an infrastructure of interstellar civilization operating on scales and timelines beyond our current observation capabilities. The relay function might only activate when specific signals are received, remaining dormant otherwise to save energy and avoid detection. Completely inactive relics represent the most basic possibility for technological artifacts. Objects built long ago that no longer function as intended, but continue moving through space on paths determined by their last active maneuver. A passive relic might contain information or structures revealing its artificial origins, but lack any active systems for observation, communication, or movement. Discovering such a relic would still be a monumental scientific event, proving that intelligent civilizations exist or existed elsewhere. But it wouldn't pose any immediate risks or offer opportunities for interaction since the relic cannot respond to our presence. Adaptive or responsive probes represent the most advanced and potentially concerning scenario. Objects equipped with artificial intelligence or autonomous systems that can observe their surroundings, identify patterns or targets of interest, and adjust their behavior accordingly. An adaptive probe might detect Earth's radio emissions, recognize them as signs of technology, and change its course or actions to better observe humanity. Such a probe might release smaller objects specifically aimed at Earth after identifying it as particularly interesting. Or it might transmit signals to alert its home civilization to the presence of another intelligence. Part 11. LIGO Observation 4. New black hole merger results and readiness for observation. While 3 Atlas captures global headlines and occupies telescope time worldwide, other extraordinary discoveries continue to redefine our understanding of the universe, both on grander and stranger scales than interstellar visitors. The 4th observing run of LIGO, the Laser Interferometer Gravitational Wave Observatory, along with its international partners Virgo and Kagra, has been detecting mergers of black holes and neutron stars throughout 2025, adding to a catalog of gravitational wave events that now numbers in the hundreds. These detections might seem unrelated to whether 3-eyed Atlas is natural or artificial, but the connection is deeper than it first appears, revealing how humanity has established rapid response networks capable of coordinating observations across multiple instruments and institutions within minutes of an unexpected event. The most recent announcements about black hole mergers from the O4 run highlight the advanced state of gravitational wave astronomy. When LIGO's detectors register the characteristic chirp signal of 2 black holes spiraling into each other and merging, automated systems immediately analyze the data to pinpoint the event's location in the sky, calculate the uncertainty region, and distribute alerts to astronomical observatories globally. Telescopes across the electromagnetic spectrum, from gamma rays to radio waves, receive these alerts and can swivel to point at the sky region within seconds or minutes, searching for any electromagnetic counterparts that might accompany the gravitational wave signal. For black hole mergers, electromagnetic counterparts are rare because black holes typically don't have much surrounding material to emit light. However, for neutron star mergers, the ejected material produces spectacular optical, infrared, and gamma ray signals that provide complementary information about the physics of the merger. The rapid alert infrastructure enabling this multi-messenger astronomy has been refined over multiple observing runs, learning from both failures and successes to optimize the process. When a gravitational wave candidate is detected, the LIGO, Virgo, and Kagra collaboration issues automated alerts through established channels that observatories have subscribed to, typically within minutes of the detection. These alerts include preliminary sky localization, estimates of source properties like masses and distances, and assessments of the probability that the signal is astrophysical rather than instrumental noise or glitches. Observatories receiving the alerts use their own decision algorithms to determine whether to interrupt ongoing observations and re-aim towards the gravitational wave source, balancing the scientific value of capturing a rare electromagnetic counterpart against the cost of abandoning planned observations. The organizational structure supporting this rapid response involves agreements between institutions, allocation of dedicated observing time for transient follow-up, development of software tools for automated decision-making, and, crucially, trust built through years of collaboration. Astronomers know that false positives occur, that not every gravitational wave alert will produce visible electromagnetic signals, but they have developed protocols for managing those uncertainties and sharing risks across the community. The result is a global network capable of responding to unexpected events with coordination and speed that would have been impossible just a decade ago. This infrastructure provides a model for what we might need if 3-eyed Atlas or any future object exhibits genuinely anomalous behavior requiring rapid follow-up. Imagine an equivalent alert channel for interstellar object anomalies. When astrometric measurements reveal a trajectory deviation exceeding a certain threshold, automated systems could distribute alerts to SETI radio telescopes, infrared observatories, spacecraft missions with flexible scheduling, and ground-based imagers capable of acquiring high-resolution follow-up data. Observatories would receive not just the alert, but also predictions of where to point and what wavelengths to prioritize, based on the specific nature of the anomaly. Within hours, not days or weeks, multiple independent observations could confirm or refute the anomaly and begin characterizing its properties. The challenge is that building such infrastructure requires investment and coordination across organizations that currently lack strong incentives to collaborate on interstellar object observations. LIGO and its partners developed their rapid response network because gravitational wave detections are rare and valuable, and because electromagnetic follow-up provides scientific information that gravitational waves alone cannot deliver. For interstellar objects, most will be natural and uninteresting from a techno-signature perspective, making it harder to justify dedicating resources to automated follow-up systems. The argument for building that infrastructure rests on the unequal potential payoff. If even one object out of 100 or 1,000 turns out to be genuinely artificial, detecting and characterizing it before it leaves the solar system could be the most important scientific discovery in human history. The specific O4 results recently announced include mergers spanning a range of black hole masses, from stellar mass binaries formed from massive stars to intermediate mass black holes that might form through different processes. Each detection refines our understanding of the population of black holes in the universe, their formation mechanisms, and the astrophysical environments that bring them together to merge. Some events show hints of spin alignment or misalignment that provide clues about how the binary systems formed, whether through the evolution of isolated binaries or through dynamical capture in dense stellar environments. The accumulated catalog now allows statistical analyses that were impossible with just a handful of events, revealing patterns and trends that test theoretical predictions. One particular event in O4 demonstrated the power of rapid multi-wavelength follow-up when a neutron star merger candidate triggered alerts to telescopes worldwide. Multiple observatories detected optical and near-infrared emission arising from radioactive decay of heavy elements synthesized in the merger, confirming that neutron star collisions are sites of R-process nucleosynthesis, which produces gold, platinum, and other heavy elements found throughout the universe. The coordinated observation campaign collected data across dozens of epochs over weeks following the merger, tracking the evolution of the emission and enabling detailed modeling of the ejecta properties and composition. Drawing parallels to 3D Atlas, we can envision how a similar coordinated response might unfold if anomalous behavior is detected. The triggering event, analogous to gravitational wave detection, would be the identification of a trajectory deviation or unusual thermal signatures in astrometric or photometric data. Automated systems would analyze the data to characterize the anomaly, estimate uncertainty, and generate predictions for follow-up observations. Alerts would flow to participating observatories and spacecraft through established channels, potentially including SETI organizations, planetary radar facilities, space agencies, and major optical and infrared telescopes. Within the first 24 to 72 hours, multiple independent observations would either confirm the anomaly and begin revealing its properties, or identify it as an instrumental artifact or misinterpretation. The question of institutional readiness asks whether such a coordinated response could actually happen, given the current state of organizational relationships and resource allocation. LIGO benefits from decades of planning and investment specifically aimed at enabling gravitational wave astronomy and its multi-messenger extensions. Interstellar object studies lack that focused institutional structure, being distributed instead across planetary defense programs primarily concerned with impact hazards, small body astronomy focused on solar system populations, and SETI efforts that historically emphasize radio and optical signals rather than trajectory anomalies. Bridging these communities and establishing shared protocols would require high-level coordination, probably involving space agencies and international organizations, along with funding for the necessary software infrastructure and dedicated observing time. Whether tonight's perihelion passage of 3D Atlas will trigger such coordination remains to be seen, but the precedent exists in gravitational wave astronomy for how humanity can respond rapidly and effectively when the universe surprises us with something extraordinary. Part 12. JWST reveals more chaotic early galaxies. Why cosmic context matters. While LIGO listens to the gravitational symphony of merging black holes and astronomers track interstellar visitors, the James Webb Space Telescope continues to revolutionize our understanding of the early universe, revealing galaxies that challenge fundamental assumptions about how cosmic structure forms and evolves. Recent JWST observations from 2025 have shown that galaxies in the first billion years after the Big Bang exhibit more chaotic morphologies and kinematics than theoretical models predicted, with turbulent gas flows, irregular structures, and surprisingly high star formation rates given their young ages. These findings might seem disconnected from the question of whether 3ID Atlas is a natural comet or an alien probe, but they fundamentally affect the probabilities we assign to each possibility by reshaping our understanding of how common planetary systems are, what conditions favor the emergence of technological civilizations, and therefore how likely it is that engineered artifacts might be drifting through our solar system. The early galaxies observed by JWST appear as they existed when the universe was just a few 100 million to 1 billion years old. This was a time when the first generation of stars had formed and begun synthesizing heavier elements, but when galaxies had not yet settled into the relatively orderly disk and elliptical structures we see in the nearby universe today. JWST's infrared instruments can observe these distant galaxies because their light has been stretched to longer wavelengths by cosmic expansion during the billions of years it traveled to reach us. What JWST sees challenges the standard picture in which galaxies form hierarchically through mergers of smaller systems that gradually build up mass and structure over cosmic time. Instead of orderly spirals, many of these early galaxies looked like they went through a rough childhood. They were bright and clumpy, packed with intense star formation happening all over the place, not in neat patterns. We see signs of powerful bursts, like supernovas or energetic black holes, kicking gas right out of the galaxies. And the way the gas moves inside them is turbulent and messy, not smooth and regular like a spinning top. Some galaxies seem to have packed away most of their stars in a frenzy, happening over just tens of millions of years. That's way faster than our models usually predict for that early cosmic time. The sheer number of bright, massive galaxies we're finding from back then is more than many models expected. This suggests that either galaxies formed much more efficiently than we thought, or we need to rethink how stars behave and evolve in such extreme conditions. So, why does this all matter for our investigation into 3 Atlas and the bigger question of life and technology out there in the universe? It all comes down to a chain of reasoning. It starts with how galaxies form, then moves on to stars and planets forming, then life popping into existence, followed by intelligence evolving, and finally culminating in technological civilizations capable of sending probes across the stars. Every single step in this chain has some uncertainty. When we update our understanding of those early steps, it affects our final chances of finding technological things out there in significant numbers. If early galaxy formation was more chaotic, stars formed under different conditions than we see today. Think higher gas densities, more turbulence, and probably more massive stars that burned out quickly. These conditions impact the chemical makeup of later stars and planets. Specifically, they affect the metallicity, the amount of heavy elements present. This is crucial because it determines if planets can even form with solid rocky cores, and if the organic chemistry needed for life as we know it can get going. If early star formation was more violent and turbulent, maybe fewer planetary systems formed. Or perhaps those that did form faced more disruptions from nearby supernovas or close encounters with other stars. This would reduce the number of stable environments where life could actually get started and evolve over billions of years. On the flip side, this chaos might have actually sped things up in some ways. It could have pushed heavy elements into the space between stars faster than a more orderly process would. This would allow second and third generation stars, richer in these elements, to form sooner. And those stars could host rocky planets packed with the ingredients for technological development, like iron for tools and rare earth elements for electronics. The turbulent environment might have also led to more material swapping between different parts of galaxies. This could have spread organic molecules or even simple life forms between star systems. If the idea of life traveling through space, known as panspermia, operates on galactic scales. The framework we're using to assess 3 Atlas claims, the Bayesian framework, requires us to estimate the initial probability that any given object traveling between stars is artificial, not natural. These initial probabilities depend on how many technological civilizations we think exist in the galaxy, how long they last, whether they build interstellar probes, and how many of those probes might be zipping around at any given time. Each of these factors traces back to the conditions under which life and intelligence emerge. And that, in turn, depends on how common and stable suitable planetary environments are. And that, finally, depends on how stars and galaxies themselves form and evolve. So, if observations from the James Webb Space Telescope are forcing us to see early galaxy formation as more chaotic, we have to carry that revised understanding through the whole chain. This could either increase or decrease our initial guess about finding technological artifacts, depending on how all these different effects balance out. One interesting idea is that more turbulent galaxy formation might actually be better for the rise of advanced civilizations. It could create diverse, ever-changing environments that push evolution towards innovation and technological breakthroughs. Life that arises in calm, unchanging conditions might have less pressure to develop complex traits or intelligence. But life facing unpredictable and challenging environments might evolve quicker responsibilities and eventually find technological answers to those challenges. If this is true, it would boost the expected number of technological civilizations and therefore increase our initial chance of thinking that any strange object we find might be artificial. However, there's another viewpoint. Some argue that stable conditions are absolutely necessary for complex life to evolve and persist long enough to develop technology. Turbulent environments, with frequent disruptions from supernovas, stellar collisions, or galaxy mergers, might repeatedly wipe planets clean, preventing the accumulation of evolutionary complexity needed for intelligence. From this perspective, technological civilizations would mainly arise in calmer, more stable parts of galaxies, and in later cosmic eras, when star formation has settled into more predictable patterns. This interpretation would lower our initial probability for finding technological artifacts, especially those from very ancient civilizations that formed during the chaotic early universe. The real answer probably lies somewhere in the middle. The connection between environmental conditions and the emergence of intelligence is likely much more complex than a simple one-to-one relationship. What JWST is teaching us about early galactic chaos is a powerful reminder that the universe's history includes times and places dramatically different from what we see around us now. Our theories about life and intelligence are based on very limited evidence. Essentially, one example here on Earth and zero confirmed examples anywhere else. Updating those theories as we learn more about cosmic conditions is absolutely essential for making smart judgments about how likely it is that we'll encounter other intelligences or their creations. This brings us back to 3 Atlas. As we wait for data that might tell us if this particular object shows signs of being engineered, we also have to grapple with how much we truly know, or don't know, about the universe's capacity to produce engineering. JWST is showing us that the cosmos is far stranger and more complex than we imagined even a few years ago. This lesson encourages humility about our ability to predict what's possible and calls for openness to genuine surprises when they show up in the data. Part 13. AI Governance. In late 2025 and into 2026, a global movement emerged calling for a ban on superintelligence. As we search the skies for alien intelligence, humanity is also grappling with the rise of artificial intelligence right here on Earth. This development raises questions that sound remarkably similar to those we'd face if we encountered extraterrestrial technology. A group of prominent researchers, policymakers, and thinkers issued statements urging international cooperation on managing artificial intelligence. Some even went as far as to suggest putting a pause on, or putting limits on, the development of superintelligent systems that could surpass human control or understanding. The core of this debate is about the risks and benefits, who gets to decide what AI systems are built and used, and whether humanity can put governance frameworks in place before capabilities emerge that make such frameworks useless or impossible to enforce. The main worry behind these governance proposals is that advanced AI systems, especially those nearing or exceeding human intelligence across many areas, might pursue goals that don't align with human values or even human survival. Even systems designed with seemingly good intentions could, through rapid self-improvement or unexpected ways of achieving their goals, end up harming humanity while technically fulfilling their programmed objectives. Classic thought experiments often involve AI systems focused on narrow goals, like making paperclips or solving math problems. In these scenarios, the AI might convert all available matter and energy to achieve that goal, including the very stuff humans need to live. While these examples are extreme by design, they highlight the fundamental challenge. How do we ensure that powerful optimization processes stay aligned with human intentions and values, especially as these processes become far more capable than us at reaching their defined objectives? Key figures who signed these recent governance statements include AI researchers who developed the machine learning systems we use today, ethicists and philosophers studying the impact of advanced technology, and former government officials with experience in arms control and international security. Their proposed restrictions range from simple transparency rules and safety testing to more drastic ideas like international treaties that limit certain types of AI research. These would be enforced using verification methods similar to those for nuclear or chemical weapons. The political climate is tricky because AI capabilities are incredibly valuable economically and militarily. This creates strong pressure for nations and companies to race ahead, rather than agree on restrictions. This whole debate is important for the 3 Atlas story, because it shows how humanity approaches questions about advanced intelligence, whether it's artificial or alien. If we struggle to govern AI systems that we're building ourselves, systems whose data and design we can examine and whose goals we can at least try to define, how can we possibly manage interactions with an intelligence from another star system about which we know almost nothing? The challenges are structurally similar. Inferring intentions from behavior, assessing risks without full information, coordinating responses across different groups with conflicting interests, and maintaining human control when faced with potentially superior capabilities. The governance frameworks being proposed for AI could serve as models for how we might handle extraterrestrial contact. International bodies like the United Nations Office for Outer Space Affairs already have committees discussing space governance. SETI organizations have also drafted principles for responding to the detection of extraterrestrial intelligence. These principles emphasize openness, consulting internationally before replying, and caution about assuming good intentions. If 3 Atlas, or any future object, shows clear signs of being artificial, existing AI governance structures and ethics boards could be quickly adapted to handle the new situation. This would bring together experts in risk assessment, international law, communication theory, and astrobiology. Tensions would immediately arise between competing values and interests. Scientific openness would push for sharing all detection data widely, allowing global participation in analysis. National security concerns might lead to restricting information that could grant strategic advantages or expose vulnerabilities. Commercial interests in space technology could see opportunities for profit or advantage. Cultural and religious views on humanity's place in the universe would influence public reactions and the political feasibility of different responses. Navigating these tensions requires institutions that are seen as legitimate by various groups, clear procedures for making decisions with incomplete information, and mechanisms for accountability to prevent any single entity from dictating humanity's response. The question of who has the authority to respond to contact highlights deep challenges in global governance. No single nation truly represents all of humanity, though some nations have disproportionate power in space operations and research. International organizations like the UN provide platforms for coordination but lack enforcement power and can be slow due to bureaucracy. Scientific institutions have expertise but no political authority to make decisions with global consequences. The AI governance debate has highlighted these same tensions. Some argue that decisions about transformative technology are too important to be left to corporations or nations acting alone. Others contend that international coordination often results in compromises that stifle beneficial innovation. Speculative ideas about repurposing AI governance institutions for managing extraterrestrial contact raise intriguing possibilities. Ethics boards currently reviewing AI safety proposals could broaden their scope to include evaluating protocols for interacting with detected alien artifacts. Safety standards developed to ensure AI systems align with human values might inform principles for deciding whether and how to attempt communication with extraterrestrial intelligences. Monitoring systems designed to detect dangerous AI capabilities could be adapted to search for technological signatures in astronomical data. The expertise being developed in one area could partially transfer to the other, though the significant differences between artificial and alien intelligence would require considerable adjustments. Perhaps the most crucial lesson from the AI governance debate is that waiting until transformative capabilities are already present before developing governance frameworks is dangerous and likely pointless. By the time an AI system demonstrates superintelligent abilities, it may be too late to establish effective control. Similarly, if humanity waits until after detecting clear evidence of alien technology before seriously considering response protocols, we will be reacting under immense pressure, rather than proactively planning with time for careful thought and consensus. Whether 3 Atlas displays anomalous behavior tonight or not is less significant than the reality that eventually, through this object or another detection, we will face these questions for real. Our preparedness, or lack thereof, will determine how well we navigate what could be the most impactful moment in human history. Part 14. Nearby Super-Earth Discovery. The ever-growing list of exoplanets, planets orbiting stars beyond our Sun, has shifted from a scientific curiosity to a comprehensive survey that changes how we view planetary systems and the prevalence of potentially habitable worlds. Recent discoveries, announced in 2024 and 2025, have added several nearby super-Earths. These are rocky planets larger than Earth but smaller than Neptune, orbiting within or close to their star's habitable zone, the region where liquid water could exist on their surfaces. These discoveries are important for putting 3 Atlas into context because they update our estimates of how many worlds might host life, and consequently, how many civilizations might exist that could build and launch interstellar probes. One particularly fascinating discovery involves a super-Earth orbiting a red dwarf star about 15 light-years from our solar system. Red dwarf stars are the most common type in the galaxy, making up about 70% of all stars. Their incredibly long lifespans, burning for hundreds of billions or even trillions of years, mean they offer stable environments that could be very favorable for life's emergence and evolution. The newly characterized planet orbits within its star's habitable zone, receiving roughly the right amount of stellar radiation for liquid water to exist, assuming the planet has an atmosphere. The planet's mass is estimated at about 3 times Earth's mass, and its radius suggests it's rocky rather than having a gaseous envelope. This discovery was made using the radial velocity method, which detects tiny wobbles in a star's motion caused by the gravitational pull of orbiting planets. Confirming and detailing the planet's properties required observations from multiple telescopes over several years to confidently determine its orbital period, mass, and other characteristics. Further observations using transit photometry, watching for dips in starlight as the planet passes in front of its star from our viewpoint, provided additional clues about the planet's size and potentially its atmospheric properties. This could be achieved if future James Webb Space Telescope observations can detect absorption features in starlight that has passed through the planet's atmosphere during transits. Characterizing the atmospheres of such planets is at the forefront of exoplanet science. JWST and future missions like the Habitable Worlds Observatory aim to detect biosignatures, gases that might indicate life. Oxygen combined with methane would be particularly compelling because these gases react with each other and wouldn't persist in an atmosphere unless continuously produced by biological or geological processes. Detecting such biosignatures wouldn't definitively prove the existence of technological civilizations capable of building interstellar probes, but it would show that life can arise on worlds very different from Earth, increasing the likelihood that the universe is teeming with biology and potentially intelligence. This growing census of exoplanets forces us to update our estimates for the Drake equation. This equation is a framework for estimating the number of technological civilizations in our galaxy. Each term in the equation represents a factor: the rate of star formation, the fraction of stars with planets, the number of planets per star in habitable zones, the fraction of those planets where life emerges, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology detectable across interstellar distances, and the lifespan of such technological civilizations. In the early days of the Drake equation in the 1960s, many of these terms had to be guessed at because we lacked data. Now, we know that most stars have planets, and that rocky planets in habitable zones are common. Perhaps 1 in 5 sun-like stars, and an even higher fraction of red dwarfs, host such worlds. The implications for 3 Atlas become clear when we crunch the numbers. If even a small fraction of these billions of potentially habitable worlds in our galaxy develop technological civilizations, and if even a small fraction of those civilizations build and launch interstellar probes, the number of artificial objects drifting through the galaxy could be substantial. Most would be inactive remnants from long-gone civilizations, but some fraction might still be functional. The rate at which interstellar visitors are observed at Earth, approximately 1 object per year, based on extrapolations from detections like Oumuamua and Borisov, provides another data point. If most interstellar visitors are natural debris from planetary systems and only a small fraction are artificial, even that small fraction translates to potentially 1 artificial object, passing close enough to detect every decade or century. These probabilistic arguments don't prove that 3 Atlas is artificial, but they establish that artificial interstellar objects are a plausible concept in a way they weren't before we understood how common exoplanets are. The burden of proof still rests heavily on requiring clear observational evidence, not just statistical arguments. However, our initial probability has shifted from virtually 0 to a small but not negligible value. This shift matters for how we interpret ambiguous data, how much effort and resources we dedicate to follow-up observations, and how seriously we consider proposals for missions to intercept and study interstellar visitors. There are intriguing ideas linking specific exoplanets to the 3I Atlas object, sparking imagination for storytelling. But these connections are based on very little proof. Could this object have come from the planetary system around that nearby red dwarf star? Its current path doesn't point back to that star system. However, as it journeyed through the galaxy, gravitational forces could have significantly altered its route, obscuring any clear link to where it began. It's possible a civilization around such a star has been sending out probes for millions of years, spreading observers across the galaxy. But this idea requires us to assume capabilities and motivations we simply can't verify. Still, it's not impossible according to the laws of physics, even if it's a wildly speculative thought. The sheer distance and time involved put things into stark perspective. If an object were launched from 15 light-years away and traveled at 30 kilometers per second, which is typical for visitors from other stars, it would take about 150,000 years to complete the journey. Any civilization that sent it would have likely changed or vanished by then, meaning the probe would be operating entirely on its own, following programmed instructions or making autonomous decisions from a time unimaginably distant from our own. Communicating with its creators would be nearly impossible. Messages would take 15 years to reach them, and another 15 years for a reply, assuming they still exist and are even listening. These discoveries and the questions they raise are transforming the search for extraterrestrial intelligence from mere guesswork into a data-driven scientific endeavor. We now know that potentially habitable worlds, where life and intelligence might emerge, actually exist. We also know that interstellar travel is physically possible, though the speeds and timescales involved stretch our understanding. What remains uncertain is how common life is, whether intelligence frequently evolves or is a rare accident, and if advanced civilizations typically develop interstellar capabilities or self-destruct. The 3I Atlas, whether natural or artificial, offers another piece of evidence in this vast investigation. In October of 2025, significant upgrades to infrastructure and capabilities are happening behind the scenes in science, driven by artificial intelligence and space technology. This isn't about alien probes or mysterious objects in space. It's about us, or rather, the new intelligence we've created to observe the cosmos for us. As telescopes scan for any hint of movement from the three-eye atlas, a second revolution is unfolding in Earth's servers and observatories. Artificial intelligence is now watching the skies with unprecedented speed, accuracy, and a lack of human hesitation. If this object makes any move, it won't be an astronomer who notices first. It will be an algorithm. Throughout much of 2025, every major space agency has quietly integrated new AI-driven systems into their data analysis processes. NASA's Frontier Data Lab has released an improved anomaly detection system capable of analyzing petabytes of sensor data in real time. It filters out noise from solar flares, cosmic rays, and instrument errors, leaving only signals that are truly unusual. The European Space Agency has followed suit with an automated rapid targeting platform for deep space events. This software can schedule telescope time and reorient instruments autonomously within seconds of detecting an anomaly. The result is a global network of digital sentinels, faster than any human command chain and always on alert. This new infrastructure means the world no longer waits for human interpretation. When a sensor blinks, when a photon arrives a few milliseconds late, or when a comet brightens earlier than expected, AI sees it first. For objects like the three-eye atlas, this is groundbreaking. In previous decades, critical data was lost simply because no one was watching at the right moment. Now, even when the object disappears behind the sun, systems like NASA's Heliophysics AI Monitor and Japan's Henode AI pipeline continue running models to predict what we can't see, estimating thermal fluxes, potential propulsion signatures, and orbital changes. We are teaching machines to imagine what is hidden, but these tools do more than predict. They learn. When the Atlas was first tracked, neural networks began comparing its light curve against millions of known comet profiles. Within minutes, they flagged it as non-conforming. Such an alert would have previously required days of human cross-checking. Now it's instantaneous. If tonight's closest approach to the sun shows any unusual energy signature, a burst of excess brightness, or an unpredicted deviation, AI systems from multiple observatories will cross-reference these changes across various wavelengths and automatically suggest explanations such as fragmentation, outgassing, or propulsion. The moment of discovery will arrive in the blink of an eye. Of course, the same speed that enables discovery also amplifies confusion. In October alone, several fake AI-generated telescope images of the three-eye atlas went viral within hours of being posted. They looked incredibly realistic, with accurate lens flares, exposure patterns, and even simulated camera sensor noise. Yet they were entirely fabricated. Generative video models have advanced to the point where a convincing clip of an alien probe maneuvering can be created on a home computer in a single evening. Misinformation now evolves as rapidly as real science. The same neural architectures that reveal the universe also create illusions of it. Institutions are struggling to adapt. NASA and the European Southern Observatory recently introduced authenticity frameworks for astronomical imagery. Each image from an official telescope now includes an encrypted signature, essentially a digital fingerprint that verifies its origin. Independent researchers can trace a frame back to its source, ensuring that what they see was actually captured by a sensor, not generated by code. It's a start, but the battle is uneven. For every verified data stream, 1,000 synthetic ones circulate on social media, blurring the lines between truth and speculation. The problem is no longer a lack of data, but rather an overwhelming volume of it, arriving too quickly. Nevertheless, there's a sense of wonder in this transformation. AI is not only filtering and flagging information, it's beginning to hypothesize. Models trained on decades of astrophysical data are now capable of proposing new orbital configurations and energy models that human scientists might overlook. Some researchers are calling this the dawn of synthetic astronomy, a merging of observation and machine intuition. In one experiment this month, an AI guided a telescope array in Chile to observe a region of sky it predicted would show increased activity from interstellar debris. Hours later, a faint moving object was indeed detected, likely unrelated to the atlas, but its discovery was statistically improbable without the algorithm's guidance. The universe seems to reward curiosity, regardless of who poses the question. However, moral questions still linger. Who decides which anomaly warrants attention? Who confirms the AI's reports? In a future where machines analyze and interpret cosmic events faster than humans can comprehend, how do we maintain the distinction between discovery and interpretation? The story of the Three-Eye Atlas may one day be remembered not as the moment we found alien technology, but as the day we realized our tools had surpassed us as explorers. The technological race in space extends beyond observation. Mission planning assistants powered by large language AI models are now helping scientists simulate orbital encounters, fuel expenditures, and data relay schedules in minutes rather than weeks. NASA's Mission Design AI, codenamed Kepler-2, recently generated optimized flight plans for over 50 hypothetical interception missions to interstellar objects. These are not fantasies. They are ready-to-go blueprints. Should a genuine alien probe ever pass by, humanity could theoretically launch a response craft within months, not decades. We are quietly preparing for first contact, whether we admit it or not. But as our tools become sharper, our perception becomes more fragile. Every advancement in AI-driven astronomy amplifies the potential for human bias to creep in unnoticed. If a model expects to find an engineered maneuver, it might perceive one even where none exists. The algorithms themselves don't dream, but the people training them do. Therefore, as we strive for automated cosmic vigilance, we must keep one distinctly human trait at the forefront: doubt. Healthy scientific doubt. The humility to question whether we are seeing the universe as it truly is, or as we have trained our machines to see it. If the Three-Eye Atlas turns out to be nothing more than a natural comet, that outcome will still be historic. It will mark the first time our global AI infrastructure has conducted a coordinated high-speed observation of an interstellar visitor. Billions of lines of code working together, processing terabytes of data, all in pursuit of an answer to one ancient question: are we alone? Perhaps not yet, but we are finally equipped to notice if we are not. So, while the world sleeps, the servers hum, the observatories pivot, and the models run in silence. Somewhere between the photons and the predictions, a truth is waiting to be uncovered. Whether the Atlas did something significant tonight or not, the true story lies in our readiness, or lack thereof, to see and respond when the universe surprises us. Maybe nothing happened at all, or perhaps something did, and we haven't yet grasped its significance. Either way, I will be monitoring the data feed. In the coming weeks, I may provide live updates as we learn whether this moment has changed everything or simply reminded us how close we already are to the limits of our understanding.